Hello everyone and welcome to Advanced Robotics. Unfortunately this year we're not able to host in-person camps due to the pandemic.
Although we don't get to meet all of you personally, we look forward to teaching everyone, and we hope that you leave the camp with more knowledge than before.
In this camp, we're going to go over the process that our robotics members go through when creating a robot.
In this summer camp, we'll be going through the process that regular members go through when creating a competition robot.
We will now go over the 5 main steps in this process, which are game strategy, CAD, building, electrical, and programming.
At the very end, we bring it all together and show it off in a demonstration where we drive the robot.
Without further ado, let's get right into today's topic, game strategy. Today is day 1 of the camp, and we're going to focus on game strategy. Game strategy is without a doubt one of the most important aspects of the entire robot creation process. It's so important because it lays the foundation for all the other steps. We're going to go over competitive robotics as a whole, watch a game reveal video, and go over game strategies that we would use. There are 3 different programs that Middleton participates in. First Tech Challenge, or FTC, First Robotics Challenge, or FRC, and VEX. FRC has 1 team, Minotaur, and FTC has 2, Masquerade and Maelstrom. VEX also has 2 teams, Minerva and Mercury. First is an organization that focuses on making STEM education accessible and engaging for students, and they do that through FTC and FRC. FTC focuses on smaller teams and robots, as well as more compact designs and subsystems due to restrictions on both team and robot size, meaning up to 15 people per team, and a robot that is up to 18 by 18 by 18 inches. FTC's build season is almost year-round, which allows for constant reiteration and progression as the season goes on. FRC, on the other hand, is about creating a larger robot with a much larger team, which is typically split up into different sub-teams in a way that is more rigid than FTC. With no limit on team size, and a much larger size restriction to work with, FRC usually works with systems that require more space and power such as pneumatics, and more complicated electronics. VEX is not organized by FIRST, but still draws some parallels to its programs. With a similar robot size and team composition to FTC, VEX teams must build their robots solely out of prefabricated VEX parts as opposed to developing custom solutions for that year's game. While it may sound like every team would have the same designs, this is far from the truth, and there is just as much excitement and innovation as any FIRST competition. VEX and FTC teams played their respective games in 2 versus 2 alliances, while FRC teams play their games in alliances of 3 each. VEX competitions also have an added skills portion, where a single team takes the field to demonstrate how well they can perform without interference from their teammates or competitors. Each program's game consists of multiple gameplay windows. FTC's game consists of 30 seconds of the robot operating completely autonomously, meaning no driver interaction. This is then followed by a 2-minute driver-controlled, or teleop, period, and the last 30 seconds of this is the endgame, where additional time-sensitive objectives can be completed to wrap up the game and earn extra points. Similarly, VEX has a 15-second autonomous period at the beginning of every round, followed by 1 minute and 45 seconds of driver control. FRC recently did away with an autonomous-only period, in favor of giving teams the option to run autonomous code, or drive the robot manually, navigating using only a camera attached directly to the robot for the first 30 seconds. This camp is going to emulate a typical FTC season, specifically last year's. Instead of fully explaining the game right away, we're going to show you the game reveal video. These videos come out at the very beginning of each season, and serve as the first exposure that teams get to that year's game. They include objectives, guidelines, and point values for various tasks. The first time around, we're going to dive right in and let you watch the video uninterrupted. Then we're going to go back and offer our own commentary on certain aspects of the game and how we would approach them. This early in the process, we try to focus mostly on the actual tasks we need to complete in the game to score the most points, and later design the specific parts we need to build for those tasks once we have our priorities worked out. These are based on how many points a task is worth, how long it will take, how consistent it would be, and several other factors. However, it's still good practice to come up with some vague ideas for how the robot will complete each portion of the game. Feel free to grab a pen and paper and try to come up with some ideas of your own the first time around. It might sound cheesy, but there's no such thing as a bad idea, especially at this point in the process. There are always teams every year that hold their own with unique, flashy designs, and even if an idea doesn't fully pan out, every suggestion is useful for brainstorming and building off of. So without further ado, here's the 2019 to 2020 season's FTC game, Skystone.
Welcome to the first Tech Challenge game for the 2019-2020 First Rise season, Skystone, presented by Qualcomm. A team consists of up to 2 driver operators, a coach, a human player, and a robot. The robot must be built from materials specified in the game manual and fit within an 18-inch sizing tool, but may expand after the match begins. Each match is played with 4 randomly selected teams, 2 per alliance. Each alliance is allowed only 1 human player. Your opponents for one match may be your partners for another. The game is played on a 12-foot square playing field with a foam tile floor and 1-foot-high walls.
8 unique navigation targets are mounted on the field walls.
Separating the landing zone from the building zone is the Sky Bridge, made up of 2 Alliance-specific bridges with 14 inches of clearance and a neutral bridge 20 inches high. Red and blue depots are taped off in the loading zone corners. Red and blue building sites are taped off in the building zone corners. Outside of the field walls are the Alliance stations and human player stations. The main game element is a stone, 4 by 8 and 5 inches tall. There are 56 stones in the game. In addition, there are 4 special sky stones, with a navigation target wrapped over one side. During gameplay, stones are assembled onto Alliance-specific foundations. These are placed in the center of the building zone, but can be moved by robots during gameplay. Each team can design and build a special capstone, which may be used to score additional points. Before each match, teams place their robots on the field, touching the wall closest to their Alliance station.
24 stones are stacked next to each human player station.
And 12 more stones are placed on the field, including 4 randomly located sky stones. Each team may preload 1 capstone onto their robot, or the human player may introduce it later in the game. Each match begins with a 30-second autonomous period. During this period, there are a number of ways for teams to score using only pre-programmed instructions and sensor inputs. Repositioning a foundation to the building site will earn 10 points for the Alliance. An Alliance earns 2 points for each stone delivered to the building zone. Both the robot and stone must be completely in the building zone. A sky stone moved into the building zone earns 10 points, only if it is the first or second sky stone delivered. After that, sky stones are worth only 2 points. If a robot can park over the midfield tape, it will earn 5 points. And finally, each stone placed in the foundation earns 2 points. Following the autonomous period is the 2-minute driver-controlled period. There are a number of ways to score points. Each stone delivered completely through an Alliance's bridge earns 1 point. However, a stone delivered through the neutral bridge does not earn any points.
Each stone placed on the foundation earns 1 point.
The last 30 seconds of the driver-controlled period is the end game. During this time, robots may continue scoring stones, but there are also ways to earn bonus points. Placing a capstone on a skyscraper will earn a 5-point bonus, plus 1 point for each level of stones. If a robot moves their foundation completely out of the building site, their Alliance earns 15 points. An Alliance will earn an additional 5 points for each robot parked in the building site. There are many ways to score in Skystone, but there are also rules that, if not followed, will award points to your opponents. For example, robots may not tip over an opponent's skyscraper. Robots cannot block access to their opponent's field elements. Robots are not allowed to reach outside of the playing field. Robots cannot launch game elements, nor are they allowed to deliberately detach parts.
This has been a brief summary of the Skystone game. For complete rules, scoring, and official field setup, please read the entire game manual and check the Q&A forum.
And always remember, the most important rule of the First Tech Challenge, gracious professionalism. Good luck, teams, and have a great season.
Now that you've had a chance to see the video, we can start to really break the game down. First things first is the autonomous period. Before we do anything, we have to realize what the main game element is. And this here, that's the stone. Those yellow blocks you saw. To score most of the points, the team needs to intake, manipulate, and outtake the blocks a specific way. Some of these blocks, 2 out of 6 to be exact, are sky stones, which have a black image overlaid on one side. In autonomous, the sky stones are very important because delivering one is worth 5 times the points of delivering a regular stone. Actually placing these stones on the foundation gives a moderate amount of points, but not as many as focusing on delivering the sky stones themselves. Now moving the foundation gives quite a few points, and it also sets the team up to be situated for fast cycle times during the teleop period. A team's cycle time is the time it takes to perform one cycle, or repetition, of that game's main scoring activity, in this case taking the block from the quarry, or the depot, to the foundation. Lastly, parking in autonomous isn't worth too many points, but it doesn't take very much time, so while teams probably shouldn't make it their first priority, it's still an important task to keep in mind. In conclusion, a team's priorities for their autonomous code should look something like this. First would be moving the foundation out of the building zone. Next, the robot should be able to recognize and deliver the sky stones as their alliance's first 2 stones under the sky bridge. After that, they would most likely want to focus on placing the sky stones on the foundation, for an extra 4 points per stone. Lastly, they should be able to park underneath the sky bridge at the end of the autonomous period, and as they refine their code to be faster, as the season goes on, they may want to try to go back for a 3rd or 4th stone, for as many points as possible. In the autonomous period, consistency is arguably more important than speed. If your program does all 5 of these things, but it only does it 20% of the time, you aren't going to be scoring nearly as many points. In this example autonomous video, the robot senses the sky stone using a color sensor. It then grabs it with a sidearm, and moves it through the bridge, and places it on the foundation for maximum points. It then goes back underneath the bridge to pick up the second sky stone, and place that one as well. Because this video was taken a bit later into the year, we were able to refine the code to the point where we could grab a 3rd block and stack that one as well. Finally, the robot turns to pull the foundation into the building zone, then parks itself under the sky bridge. Next is a teleop or driver-controlled period, which is where the majority of the match time is spent. Here stones have to be taken from the depot side, delivered completely through the sky bridge, and be placed onto the foundation for maximum points. Now here we have the benefit of hindsight. While it would be possible for both robots to go to the depot, collect a stone, and drive all the way back to stack it would be much more efficient to divide this journey in half. As alliances have 2 team members, they would be able to make one team a feeder, which would take stones from the depot and deliver them under the sky bridge to the stacker, which would be the other team on the alliance. The stacker would then take blocks from the feeder, with minimal movement because the feeder has already delivered the blocks, and places them onto the foundation, stacking them on top of other stones as the game goes on. As teams went through the season, they quickly discovered that this method of having a feeder and a stacker was far more efficient than just having both teams go at it on their own. This specialization between the 2 teams allows each team to focus on designs that would help them with their specific task. For example, while a stacker might want a stable but heavy vertical lift in order to stack the blocks as high as possible, a feeder would most likely benefit more from a more simple but lightweight design in order to maximize their speed. Furthermore, because most stacking points come from the height of the skyscraper, stackers should focus on single block towers, as this would be the most efficient design for creating the tallest possible stacks in the shortest possible time. When it comes to capping, the stacker should be able to cap their tallest structure. However, a feeder may not have the facilities for this, but they would still get a portion of the points for putting their capstone on a smaller stack or the foundation itself. In the endgame, alliances have the option to move their foundation back into the building area. This gives an impressive 15 points. However, the team runs the risk of knocking their stack over, which could cause them to lose points. And like an autonomous, parking is a quick but simple way to boost your points. In conclusion, the teleop period should be about getting cycle times down as fast as possible. For this, alliances would need to have chemistry between the feeder and stacker, so that each team knows what the other is doing, and they can plan accordingly. There should also be minimal downtime for the stacker. If possible, they should always have at least 1 block ready to be stacked, maybe even 2 or 3 depending on the speed of the feeder. During the endgame, the stacker should try to cap the tallest stack possible, but if the feeder isn't able to, they should focus on capping a smaller stack or the foundation itself. Finally, in the endgame, the stacker should be the robot to move the foundation back into the building zone because they're the closest to it, and both teams should try to park if they can. And with that, we're going to just about wrap up Day 1 of Advanced Robotics. Our next video, Day 2, is going to cover our design process, as well as computer-aided design, or CAD software, which we use to make custom 3D models of parts and assemblies. Again, we're sorry we're not able to host in-person camps this year due to the pandemic, but we're still excited to be able to share a portion of the robotics experience. And we thank you all for taking time out of your summer and being so flexible. Take care, everyone, and never stop learning.